percent, Asia, page, page, Africa.
Is that the right answer or the wrong answer?
Nose. Question. Difficult. Question. 4. Wrong.
Is there an example on page 3? Is this the right page?
Did she choose the right answer?
Don't worry, you will do well on the next test.
We need to take 5 reading lessons. We need to take 5 reading lessons. We need to take 5 reading lessons.
The listening test was harder than the speaking test. The listening test was harder than the speaking test. Yes, I took the test yesterday. I was 20 minutes late, but I finished it. Ben, you did very well on the test, right? Yes, I took the test yesterday. I was 20 minutes late, but I finished it. Ben, you did very well on the test, right?
Lucy takes English lessons after school. 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 Lucy takes English lessons after school.
Ben, did you forget to write your name on the listening test? This test is very good, but there isn't a name.
Did you choose the wrong answer?
What time is your art lesson?
Writing is the hardest.
How do you say this English word? 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 How do you say this English word?
Lucy takes English lessons after school. Lucy takes English lessons after school. Lucy takes English lessons after school. Lucy takes English lessons after school.
Face.
Bus.
Station.
Plane.
Face.
This is my child.
This hat is nice. Hot. Hat.
We have a meeting with Ben this morning. 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 We have a meeting with Ben. We have a meeting with Ben this morning. We have a meeting with Ben this morning. We have a meeting with Ben this morning.
Her hair is not very clean now. Her hair is not very clean now.
Clean. Queen.
Her hair is not very clean now.
Clean. Queen. Clean.
My grandpa loves his dog very much. 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 My grandpa loves his dog very much.
He has one child.
My son never eats breakfast.
Is our meeting this evening? Is our meeting this evening? Is our meeting this evening? Is our meeting this evening?
Is our meeting this evening? It is 3 o'clock. It is 3 o'clock. It is 3 o'clock. It is 3 o'clock. It is 3.
I love my son very much. I love my son very much.
We have a meeting with Ben this morning. We have a meeting with Ben this morning.
America. Math.
Camera. Camera. Doctor.
Yes, I am from America, and you?
Do we need to take a test now? Talk. Take.
His parents didn't feel well yesterday. 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 His parents didn't feel well yesterday.
I need to take a test? Talk. Take.
Ms. Nguyen is our Vietnamese teacher. 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 Ms. Nguyen is our Vietnamese teacher.
I speak English. I speak English.
I speak Vietnamese and some English.
Ms. White is the youngest teacher in our Ms. White is the youngest teacher in our school.
From my house to my office.
Ms. Nguyen is our Vietnamese teacher. Ms. Nguyen is our Vietnamese teacher. Subject:
Desk.
blackboard.
Boot.
Are you from Hanoi?
Six t-shirts and 6 skirts. 6. Speaks. 6.
How many horses do you have, Mr. Tran? 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 Horse do you have, Mr. Tran?
We want 6 skirts.
Are you from Vietnam? Are you from Vietnam?
Right foot.
Hello.
This bird's left foot and right foot are different.
I am from America. I'm from Ho Chi Minh City.
Hanoi, Ho Chi Minh City.
Are you from Hanoi?
No, they are not. Juice. Drinking. Juice. Apple. Juice.
I like to read funny books. I like to read funny books.
Dad. Reading.
They're cooking Japanese noodles.
This food isn't hot. This food isn't hot. This food isn't hot. This food isn't hot. This food isn't hot.
My dog loves him. My dog loves him.
Dad. Reading. Now.
My daughter's son is washing the dishes.
I am watching a movie now. I am watching a Chinese movie now. I am watching a Chinese movie now.
Mother-to-be. Mother-to-be. Pregnant. Pregnant.
Present continuous. Use. We use the present simple to talk about things we do or that happen regularly. We use the present continuous to talk about something in progress in the present. This can be something actually in progress at this moment.
I can't answer the phone because I'm driving.
Something happening around now, but not necessarily at this moment.
I'm looking for a new job.
A changing situation.
More and more people are changing their diet.
Form. We form the present continuous with be plus verb plus ing. I.
I'm writing. I'm not writing. Am I writing?
You, we, they.
We're writing. They aren't writing. Are you writing?
He, she, it.
He's writing. She isn't writing. Is she writing?
Some verbs describe states. For example, agree, believe, hate, know, like, love, prefer, want. We don't use these verbs with the continuous. We don't say, he's owning a really nice car. We do say, he owns a really nice car. Present continuous. Use. We use the present simple to talk about things we do or that happen regularly. We use the present continuous to talk about something in progress in the present. This can be something actually in progress at this moment.
I can't answer the phone because I'm driving.
Something happening around now, but not necessarily at this moment.
I'm looking for a new job.
A changing situation.
More and more people are changing their diet.
Form. We form the present continuous with be plus verb plus ing. I, they.
Are you writing?
Love, prefer.
So we've been inching closer and closer to that holy grail of data structures, one that we can insert into, delete from, and look up in constant time, right? That's sort of the goal. We want to be able to do things very, very quickly. Have we found it here when we're talking about tries? Well, let's take a look. So we've seen several different data structures that handle the mapping of so-called key-value pairs, mapping some piece of data to some other piece of data so we know where to find information in a structure. So for an array, for example, the key is the element index, array location 0, array location 1, and so on. And the value is the data that exists at that location. So what is stored in array 0? What is stored in array 1 versus just 0 and 1, which would be the keys? With a hash table, it's sort of the same idea. With the hash table, we have this hash function that generates hash codes. So the key is the hash code of the data, and the value, particularly when we talked about chaining in the video on hash tables, is that linked list of data that hashes to that hash code, right? What about another approach to this method, though? What about a method where the key is guaranteed to be unique, unlike a hash table where we could end up with two pieces of data having the same hash code, and then we have to deal with that by either probing or more preferably chaining to fix that problem. So now we can guarantee that our key will be unique. And what if our value was just something as easy as true and false that tells us whether or not that piece of information exists in the structure? A Boolean could be as simple as a bit. Realistically, it's probably a byte more likely than a bit. But that's a lot smaller than storing maybe a 50-character string, for example. So tries, similar to hash tables, which combine arrays and linked lists, tries combine arrays, structures, and pointers together to store data in an interesting way that's pretty different from anything we've seen so far. Now, we use the data as a roadmap to navigate this data structure. And if we can follow the roadmap, if we can follow the data from beginning to end, we'll know whether that data exists in the try. And if we can't follow the map from beginning to end at all, the data can't exist. Again, the keys here are guaranteed to be unique. And so unlike a hash table, we'll never have to deal with collisions here. And no two pieces of data have exactly the same roadmap unless that data is identical. If we insert John and then we search for John, that's two identical pieces of data, right, we're looking through. But otherwise, any two pieces of data are guaranteed to have unique roadmaps through this data structure. And we're going to take a look at a visual of this in just a moment. We'll do this by trying to create a new data structure mapping the following key value pairs. In this case, we're not going to use something as simple as a Boolean. We actually will store the string, and that string is going to be the name of a university, and the key is going to be the year when that university was founded. All years for universities are going to be 4 digits. And so we'll use those 4 digits to navigate through this data structure. And we'll see again how we do that in just a second. And at the end of the path, we'll see the name of the university that corresponds to that key, those 4 digits. The basic idea behind a try is we have a central root. So think about it like a tree, and this is similar in spelling and in concept to a tree. Generally, when we think about trees in the real world, they have a root that's in the ground, and they grow upward, and they have branches, and they have leaves. And basically, the idea of a try is exactly the same, except that the root is anchored somewhere up in the sky, and the leaves are at the bottom. So it's kind of like taking a tree and just flipping it upside down. But there are still branches, and those would be our pathways, those would be our connections from the root to the leaves. In this case, those paths, those branches, are labeled with digits that tell us which way to go from where we are. If we see a 0, we go down this branch. If we see a 1, we go down this branch, and so on and so on. Well, what does this mean? Well, that means that at every junction point, at every node in the middle, at every branch, there are 10 possible places that we can go. So there are 10 pointers from every location. And this is where tries can get a little bit intimidating for somebody who's never really doesn't have a lot of experience in computer science before. But tries are really pretty awesome, and if you have the chance to work with them and you're willing to sort of dig in and experiment with them, they're really quite interesting data structures to work with. If we want to insert an element into the trie, all we need to do is build the correct path from the root to the leaf. Here's what every step along the way might look like. We're going to define a new data structure for a new node called a trie. And inside of that data structure, there are two pieces. We're going to store the name of a university, and we're going to store an array of pointers to other nodes of the same type. So again, this is that sort of concept of everywhere we are, we have 10 possible places we can go. If we see a 0, we go down this branch. If we see a 1, this branch, and so on and so on and so on. If we see a 9, we go down this branch. So at every junction point, we can go 10 possible places. So every node has to contain 10 pointers to other nodes, to 10 other nodes. And the data we're storing is just the name of the university. So let's build a trie. Let's insert a couple of items into our trie. So at the very top, this is our root node. This is probably going to be something you're going to globally declare, and you're going to globally maintain a pointer to this node always. You're going to say root equals, and you're going to malloc yourself a trie node, and you're never going to touch root again. Every time you want to start navigating through, you set another pointer equal to root, and you use, like such as trav, which is the example I use in many of my videos here on stacks and queues and linked lists and so on. You set another pointer called trav for traversal, and you use trav to navigate through the data structure. So let's see how this might look. So right now, what does a node look like? Well, just as our data structure declaration indicated, we have a string, which in this case is empty, there's nothing here, and an array of 10 pointers. And right now, we only have one node in this trie. There's nothing else in it, so all 10 of those pointers point to null. That's what the red indicates. Let's insert the string Harvard. Let's insert the University of Harvard into this trie, which was founded in the year 1636. We want to use the key 1636 to tell us where we're going to store Harvard in the trie. Now, how might we do that? It might look something like this. We start at the root, and we have these 10 places we can go. The root is just like any other node of the trie. There are 10 places we can go from here. Where do we probably want to go? If the key is 1636, there's really two options, right? We could build the key from right to left and start with 6, or we could build the key from left to right and start with 1. It's probably more intuitive as a human being to understand we'll just go left to right. And so if I want to insert Harvard into this trie, I probably want to start by starting at the root, looking at my 10 options in front of me and saying, I want to go down the 1 path, okay? Now, 1 path is currently null. So if I want to proceed down that path to insert this element into the trie, I have to malloc a new node, have 1 point there, and then I'm good to go. So I basically am at a point where I'm standing at the root of the tree, of the trie, and there are 10 branches, but each branch has a gate in front of it, right? Because there's nothing else there. There's no safe passage. That means that there's nothing down any of those branches. If I want to start building something, I want to remove the gate. I want to remove the gate in front of number 1, and I want to walk down that, and I want to build another place for me to go. And that's what I've done here. So 1 no longer points to null. I've said it's safe to go down here now. I've built another node, and when I get to that node, I have another decision to make. Where am I going to go from here? Well, I've already gone down the 1, so now I probably want to go down the 6, right? Again, I have 10 locations I can choose, so let's now go down number 6. So I clear the gate in front of number 6, and I walk down there, and I build another node, and I've reached another junction point. Again, I have 10 choices for where I can go. I've moved from 1 to 6, so now I probably want to go to 3. 3, there's nowhere I can go, so I have to clear the way and build myself a new space. And then from 3, where do I want to go? I want to go down 6. And again, I had to clear the way to do it. So now I've used my key to create nodes and start to build this trie. I've started at the root, I've gone down 1, 6, 3, 6. And now I'm at the bottom there in that node, and you might be able to see it on your screen. It's highlighted in yellow. That's where I currently am. My key is done. I've exhausted every position in my key, so I can't go any further. So at this point, all I really need to do is say, okay, sort of like looking down at the ground, if you're envisioning yourself as this sort of path with different connections, sort of looking down and sort of like spray painting Harvard on the ground. That's the name of this node. That's what's at this location. If we start at the root and we go down 1 and then 6 and then 3 and then 6, where are we? Well, if we look down and we see Harvard, then we know that Harvard was founded in 1636 based on the way we're implementing this data structure. So that was hopefully straightforward. We're going to do 2 more insertions, and hopefully it'll help to see this done twice more. Now let's insert another university. Let's insert Yale into this try. Yale was founded in 1701. So we'll start at the root as we always do, and we set a traversal pointer. We're going to use that to move through. The first thing we want to do is go down the 1 path. That's the first digit of our key. Fortunately, though, we don't have to do any work this time. The 1 path has already been cleared. I cleared it previously when I was inserting Harvard at 1636. So I can safely move down 1 and just go there. I can move to down the 1. Now, though, I want to go to 7. I cleared the way at 6. I know I could safely proceed down the 6 path, but I need to proceed down the 7 path. So what do I need to do? Well, just like before, I just need to clear the gate, have it get out of the way, and build a new node from the 7 path, just like this. So now I've moved 1 and then 7. And now notice I'm sort of on this new sub-branch, right? Everything else from 16 on, I don't care about. I'm not doing 16 anything, I'm doing 17 stuff. So now, from 17 on, I have to sort of blaze new trails here. The next digit of my key is 0. I clearly can't get anywhere. I just built this node, so I know there's no paths forward from here, so I have to make one myself. So I malloc a new node and have 0 point there. And then one more time, I malloc a new node and have 1 point there. Again, I've exhausted my key, 1701. So I look down and I spray paint Yale on, that's the name of this node. And so now if I ever need to see if Yale is in this try, I start at the root, I go down 1701 and look down, and if I see Yale spray painted onto the ground, then I know Yale exists in this try. Let's do one more. Let's insert Dartmouth into this try, which was founded in 1769. Start at the root again. My first digit of my key is 1. I can safely move down that path that already exists. The next digit of my key is 7. I can safely move down that path. It exists as well. My next digit is 6. From here, from where I currently am in yellow there in that middle node, 6 is currently locked off. I need to, if I want to go down that path, I have to build it myself. So I'll malloc a new node and have 6 point there. And then again, I'm blazing new trails here. So I malloc a new node so that from that node, path number 9, and then now if I travel 1769, and I look down, there's nothing currently spray painted there. I can write Dartmouth, and I've inserted Dartmouth into the try. So that's inserting things into the try. Now we want to search for things. How do we search for things in the try? Well, it's pretty much the same idea. Now we just use the digits of the key to see if we can navigate from the root to where we want to go in the try. If we hit a dead end at any point, then we know that that element can't exist, or else that path would have already been cleared. If we make it all the way to the end, all we need to do is look down and see if that's the element we're looking for. If it is, success. If it's not, fail. So let's search for Harvard in this try. We start at the root, and again, we're going to create a traversal pointer to do our moves for us. From the root, we know that the first place we need to go is 1. Can we do that? Yes, we can. It safely exists. We can go there. Now, the next place we need to go is 6. Does the 6th path exist from here? Yeah, it does. We can go down the 6th path, and we end up here. Can we go down the 3 path from here? Well, as it turns out, yes, that exists too. And can we get on the 6th path from here? Yes, we can. We haven't quite answered the question yet. There's still one more step, which is now we need to look down and see if that's actually, if we're looking for Harvard, is that what we find after we exhaust the key? In the example we're using here, the years are always 4 digits, but you might be using an example where you are storing a dictionary of words. And so instead of having 10 pointers from every location, you might have 26, one for each letter of the alphabet. And there are some words like bat, which is a subset of batch, for example. And so even if you get to the end of the key and you look down, you might not see what you're looking for. So you always have to traverse the entire path. And then, if you are successfully able to traverse the entire path, look down and do one final confirmation. Is that what I'm looking for? Well, I look down after starting at the top and going 1, 6, 3, 6. I look down, I see Harvard. So yes, I succeeded. What if what I'm looking for isn't in the try, though? What if I'm looking for Princeton, which was founded in 1746? And so 1746 becomes my key to navigate through the try. Well, I start at the root, and the first place I want to go is down the 1 path. Can I do it? Yes, I can. Can I go down the 7 path from there? Yeah, I can. That exists too. But can I go down the 4 path from here? That's like asking the question, can I proceed down that little square that I've highlighted in yellow? There's nothing there, right? There's no way forward down the 4 path. If Princeton was in this try, that 4 would have been cleared for us already. And so at this point, we've reached a dead end. We can't go any further. And so we can say definitively, no, Princeton does not exist in this try. So what does this all mean, right? There's a lot going on here. There's pointers all over the place, and as you can see just from the diagram, there's a lot of nodes that are kind of flying around. But notice, every time we wanted to check whether something was in the try, we only had to look at we only had to make 4 moves. Every time we want to insert something into the try, we have to make 4 moves, possibly mallocing some stuff along the way. But as we saw when we inserted Dartmouth into the try, sometimes some of the path might already be cleared for us. And so as our try gets bigger and bigger, we have to do less work every time to insert new things because we've already built a lot of the intermediate branches along the way. If we only ever have to look at 4 things, 4 is just a constant, we really are kind of approaching constant time insertion and constant time lookup. The trade-off, of course, being that this try, as you can probably tell, is huge. Each one of these nodes takes up a lot of space, but that's the trade-off. If we want really quick insertion, really quick deletion, and really quick lookup, we have to have a lot of data flying around. We have to set aside a lot of space in memory for that data structure to exist. And so that's the trade-off, but it looks like we might have found it. We might have found that holy grail of data structures with quick insertion, deletion, and lookup. And maybe this will be an appropriate data structure to use for whatever information we're trying to store. I'm Doug Lloyd. This is CS50. That we can use to maintain data in an organized way. Similar to a stack, it can be implemented as an array or a linked list. Unlike a stack, the rules that we use to determine when things get added and removed from a queue are a little bit different. Unlike a stack, which is a LIFO structure, last in, first out, a queue is a FIFO structure, FIFO, first in, first out. Now, queues, you probably have an analogy to queues if you've ever been in line at an amusement park or at a bank. There's sort of a fairness implementing structure, right? The first person in line at the bank is the first person who gets to speak to the teller. It would be sort of a race to the bottom if the only way you got to speak to the teller at the bank was to be the last person in line. Everybody would always want to be the last person in line. And the person who was there first, who has been waiting for a while, could be there for hours and hours and hours before they have a chance to actually withdraw any money at the bank. And so queues are sort of the fairness implementing structure. But that doesn't necessarily mean that stacks are a bad thing, just that queues are another way to do it. So again, a queue is first in, first out versus a stack, which is last in, first out. Similar to a stack, we have 2 operations that we can perform on queues. The names are enqueue, which is to add a new element to the end of the queue, and dequeue, which is to remove the oldest element from the front of the queue. So we're going to add elements onto the end of the queue, and we're going to remove elements from the front of the queue. Again, with a stack, we were adding elements to the top of the stack and removing elements from the top of the stack. So with enqueue, it's adding to the end, removing from the front. So the oldest thing in there is always the next thing to come out if we try and dequeue something. So again, with queues, we can have array-based implementations and linked list-based implementations. We'll start again with array-based implementations. The structure definition looks pretty similar. We have another array there of data type value, so it can hold arbitrary data types. We're again going to use integers in this example. And just like with our array-based stack implementation, because we're using an array, we necessarily have that limitation that C kind of enforces on us, which is we don't have any dynamism in our ability to grow and shrink the array. We have to decide at the beginning what is the maximum number of things that we can put into this queue. And in this case, capacity would be some pound-defined constant in our code. And for purposes of this video, capacity is going to be 10. We need to keep track of the front of the queue so we know which element we want to dequeue. And we also need to keep track of something else, the number of elements that we have in our queue. Notice we're not keeping track of the end of the queue, just the size of the queue. And the reason for that will hopefully become a bit clear in a moment. Once we have completed this type definition, we have a new data type called Q, which we can now declare variables of that data type. And somewhat confusingly, I've decided to call this Q, the letter Q instead of the data type Q. So here is our Q. It is a structure. It contains 3 members or 3 fields, an array of size capacity. In this case, capacity is 10, and this array is going to hold integers. In green is the front of our queue, the next element to be removed. And in red will be the size of the queue, how many elements are currently existing in the queue. So if we say q.front equals 0 and q.size equals 0, we're putting zeros into those fields. And at this point, we're pretty much ready to begin working with our queue. So the first operation we can perform is to enqueue something, to add a new element to the end of the queue. Well, what do we need to do in the general case? Well, this function enqueue needs to accept a pointer to our queue. Again, if we had declared our queue globally, we wouldn't need to do this necessarily. But in general, we need to accept pointers to data structures like this, because otherwise we're passing by value, we're passing in copies of the queue, and so we're not actually changing the queue that we intend to change. The other thing it needs to do is accept a data element of the appropriate type. Again, in this case, it's going to be integers, but you could arbitrarily declare the data type as value and use this more generally. That's the element we want to enqueue. We want to add to the queue, to the end of the queue. Then we actually want to place that data in the queue, in this case, placing it in the correct location of our array. And then we want to change the size of the queue, how many elements we currently have. So let's get started. Here's again that general form function declaration for what enqueue might look like. And here we go. Let's enqueue the number 28 into the queue. So what are we going to do? Well, the front of our queue is at 0 and the size of our queue is at 0. And so we probably want to put the number 28 in array element number 0, right? So we've now placed that in there. So now what do we need to change? We don't want to change the front of the queue because we want to know what element we might need to dequeue later. So the reason we have front there is sort of an indicator of what's the oldest thing in the array. Well, the oldest thing in the array, in fact, the only thing in the array right now, is 28, which is at array location 0. So we don't want to change that green number because that's the oldest element. Rather, we want to change the size. So in this case, we'll increment size to 1. Now, a general sort of idea of where the next element is going to go in a queue is to add those two numbers together, front and size. And that'll tell you where the next element in the queue is going to go. So now let's enqueue another number. Let's enqueue 33. So the 33 is going to go into array location 0 plus 1. So in this case, it's going to go into array location 1. And now the size of our queue is 2. Again, we're not changing the front of our queue because 28 is still the oldest element. And we want to, when we eventually get to dequeuing, removing elements from this queue, we want to know we want to know where the oldest element is. And so we always need to maintain some indicator of where that is. So that's what the 0 is there for. That's what front is there for. Let's enqueue one more element, 19. I'm sure you can guess where 19 is going to go. It's going to go into array location number 2. That's 0 plus 2. And now the size of our queue is 3. We have 3 elements in it. So if we were to, and we're not going to right now, enqueue another element, it would go into array location number 3, and the size of our queue would be 4. All right, so we've enqueued several elements now. Now let's start to remove them. Let's dequeue them from the queue. So similar to pop, which is sort of the analog of this for stacks, dequeue needs to accept a pointer to the queue, again, unless it's globally declared. Now we want to change the location of the front of the queue. This is where it sort of comes into play, that front variable, because once we remove an element, we want to move it to the next oldest element. Then we want to decrease the size of the queue, and then we want to return the value that was removed from the queue. Again, we don't want to just discard it. We presumably are extracting it from the queue. We're dequeuing it because we care about it. So we want this function to return a data element of type value. Again, in this case, value is integer. All right, so now let's dequeue something. Let's remove an element from the queue. If we say int x equals dequeue ampersand q, again, that's a pointer to this queue data structure, what element is going to be dequeued? In this case, because it is a first in, first out data structure, FIFO, the first thing we put into this queue was 28. And so in this case, we're going to take 28 out of the queue, not 19, which is what we would have done if this was a stack. We're going to take 28 out of the queue. Similar to what we did with a stack, we're not actually going to delete 28 from the queue itself. We're just going to kind of pretend it isn't there. So it's going to stay there in memory, but we're just going to kind of ignore it by moving the other two fields of our queue data structure. We're going to change the front, queue.front is now going to be 1, because that is now the oldest element we have in our queue, because we've already removed 28, which was the former oldest element. And now we want to change the size of the queue to 2 elements instead of 3. Now remember earlier I said when we want to add elements to the queue, we put it in array location, which is the sum of front and size, right? So in this case, we're still putting the next element in the queue, into array location 3. And we'll see that in a second. So we've now dequeued our first element from the queue. Let's do it again. Let's remove another element from the queue. In this case, the current oldest element is at array location 1. That's what queue front tells us. That green box tells us that that's the oldest element. And so x will become 33. We'll just kind of forget that 33 exists in the array. And we'll say that now the new oldest element in the queue is at array location 2. And the size of the queue, the number of elements we have in the queue, is 1. Now let's enqueue something. And I sort of gave this away a second ago, but if we want to put 40 into the queue, where's 40 going to go? Well, we've been putting it in queue front plus queue size, and so it makes sense actually to put 40 here. Now, notice that at some point we're going to get to the end of our array inside of queue, but that faded out 28 and 33, they're actually technically open spaces, right? And so we may eventually, that rule of adding those two together, we may eventually need to mod by the size of capacity so we can wrap around. So if we get to element number 10, if we'd be placing it in element number 10, we'd actually put it in array location 0. And if we were getting to array location, or excuse me, if we added them up together and we got to number 11 would be where we would have to put it, which doesn't exist in this array, would be going out of bounds. We could mod by 10 and put it in array location 1. So that's how queues work. They're always going to go from left to right and possibly wrap around. And you know that they're full if size, that red box, becomes equal to capacity. And so after we've added 40 to the queue, well, what do we need to do? Well, the oldest element in the queue is still 19, so we don't want to change the front of the queue. But now we have 2 elements in the queue, and so we want to increase our size from 1 to 2. That's pretty much it with working with array-based queues, and similar to stacks, there is also a way to implement a queue as a linked list. Now, if this data structure type looks familiar to you, it is. It's not a singly linked list, it's a doubly linked list. And now, as an aside, it is actually possible to implement a queue as a singly linked list, but I think in terms of visualization, it actually might help to view this as a doubly linked list, but it is definitely possible to do this as a singly linked list. So let's have a look at what this might look like. If we want to enqueue, so now, again, we're switching to a linked list-based model here. If we want to enqueue, we want to add a new element, well, what do we need to do? Well, first of all, because we're adding to the end and removing from the beginning, we probably want to maintain pointers to both the head and the tail of the linked list, tail being another term for the end of the linked list, the last element in the linked list. And these will probably, again, be beneficial to us if they are global variables. But now if we want to add a new element, what do we have to do? Well, we just malloc or dynamically allocate our new node for ourselves. And then, just like when we add any element to a doubly linked list, we just have to sort of, those last 3 steps here are just all about moving the pointers in the correct way so that the element gets added to the chain without breaking the chain or making some sort of mistake or having some sort of accident happen whereby we accidentally orphan some elements of our queue. Here's what this might look like. We want to add the element 10 to the end of this queue. So the oldest element here is represented by head. That's the first thing we put into this hypothetical queue here. And tail, 13, is the most recently added element. And so if we want to enqueue 10 into this queue, we want to put it after 13. And so we're going to dynamically allocate space for a new node and check for null to make sure we didn't have a memory failure. Then we're going to place 10 into that node. And now we just need to be careful about how we organize pointers so we don't break the chain. We can set 10's previous field to point back to the old tail. And since 10 will be the new tail at some point by the time all of these chains are connected, there's nothing's going to come after 10 right now. And so 10's next pointer will point to null. And then after we do this, after we've connected 10 backwards to the chain, we can take the old head, or excuse me, the old tail of the queue, the old end of the queue, 13, and make it point to 10. And now at this point, we have enqueued the number 10 into this queue. All we need to do now is just move the tail to point to 10 instead of to 13. Dequeuing is actually very similar to popping from a linked list, from a stack that is implemented as a linked list. If you've seen the stacks video, all we need to do is start at the beginning, find the second element, free the first element, and then move the head to point to the second element. Probably better to visualize it just to be extra clear about it. So here's our queue again. 12 is the oldest element in our queue, the head. 10 is the newest element in our queue, our tail. And so when we want to dequeue an element, we want to remove the oldest element. So what do? Well, we set a traversal pointer that starts at the head and we move it so that it points to the second element of this queue. Something by saying trav equals trav arrow next, for example, would move trav there to point to 15, which after we dequeue 12 or after we remove 12 will become the then oldest element. Now that we've got a hold on the first element via the pointer head and the second element via the pointer trav, we can now free head. And then we can say nothing comes before 15 anymore, so we can change 15's previous pointer to point to null. And we just move the head over. And there we go. Now we have successfully dequeued 12, and now we have another queue of 4 elements. That's pretty much all there is to queues, both array-based and linked list-based. I'm Doug Lloyd. This is CS50. All right, so by this point, you're probably pretty familiar with arrays and linked lists, which are the two primary data structures we've talked about for keeping sets of data of similar data types organized. Now we're going to talk about a couple of variations on arrays and linked lists. And in this video, we're going to talk about stacks. Specifically, we're going to talk about a data structure called a stack. Recall from couple of variations on arrays and linked lists. And in this video, we're going to talk about stacks. Specifically, we're going to talk about a data structure called a stack. Recall from previous discussions about pointers and memory that the stack is also the name for a segment of memory where statically declared memory that you name, variables that you name, etc., and function frames, which we also call stack frames, exist. So this is a stack data structure, not a stack segment of memory. Okay, but what is a stack? So it's pretty much just a special kind of structure that maintains data in an organized way. And there's two very common ways to implement stacks using two data structures that we're already familiar with, arrays and linked lists. What makes a stack special is the way in which we put information into the stack and the way we remove information from the stack. In particular, with stacks, the rule is only the most recently added element can be removed. So think about it as if it's a stack. We're sort of piling information on top of itself, and only the thing at the top of the pile can be removed. We can't remove the thing underneath because everything else would collapse and fall over. So we really are building a stack that we then have to remove piece by piece. Because of this, we commonly refer to a stack as a LIFO structure, last in, first out, LIFO, last in, first out. So because of this restriction on how information can be added to and removed from a stack, there's really only two things we can do with a stack. We can push, which is the term we use for adding a new element to the top of the stack, or if the stack doesn't exist and we're creating it from scratch, creating the stack in the first place would be pushing. And then pop, that's the sort of CS term we use to remove the most recently added element from the top of the stack. So we're going to look at both implementations, both array-based and linked list-based, and we're going to start with array-based. So here's the basic idea of what the array-based stack data structure would look like. We have a type definition here. Inside of that, we have two members or fields of the structure. We have an array, and again, I'm using the arbitrary data type value, so this could be any data type, int, char, or some other data type you've previously created. So we have an array of size capacity being a pound-defined constant, perhaps somewhere else in our file. So notice already with this particular implementation, we are bounding ourselves, as was typically the case with arrays, which we cannot dynamically resize, where there's a certain number of elements maximum that we can put in our stack. In this case, it's capacity elements. We also keep track of the top of the stack. What element is the most recently added to the stack? And so we keep track of that in a variable called top. And all of this gets wrapped up together into a new data type called a stack. And once we've created this new data type, we can treat it like any other data type. We can declare stack s, just like we could do int x or char y. And when we say stack s, well, what happens is we get a set of memory set aside for us. In this case, capacity I've apparently decided is 10 because I've got a single variable of type stack, which contains two fields, recall, an array, in this case it's going to be an array of integers, as is the case in most of my examples, and another integer variable capable of storing the top, the most recently added element to the stack. So one single stack of what we just defined looks like this. It's a box containing an array of 10, what will be integers in this case, and another integer variable there in green to indicate the top of the stack. To set the top of the stack, we just say s.top. That's how we access a field of a structure, recall. s.top equals 0 effectively does this to our stack. So again, we have two operations that we can perform now. We can push and we can pop. Let's start with push. Again, pushing is adding a new element to the top of the stack. So what do we need to do in this array-based implementation? Well, in general, the push function is going to need to accept a pointer to the stack. Now, take a second and think about it. Why would we want to accept a pointer to the stack? Recall from previous videos on variable scope and pointers, what would happen if we just sent stack, s rather, in as a parameter? What would actually be passed in there? Remember, we're creating a copy when we pass it to a function, unless we use pointers. And so we need to accept, this function push needs to accept a pointer to the stack so that we're actually changing the stack we intend to change. The other thing push probably wants to accept is a data element of type value, in this case, again, integer, that we're going to add to the top of the stack. So we've got our two parameters. What are we going to now do inside of push? Well, simply, we're just going to add that element to the top of the stack and then change where the top of the stack is, that s.top value. So this is what a function declaration for push might look like in an array-based implementation. Again, this isn't a hard and fast rule that you could change this and have it vary in different ways. Perhaps s is declared globally, and so you don't even need to pass it in as a parameter. This is, again, just a general case for push, and there are different ways to implement it. But in this case, our push is going to take two arguments, a pointer to a stack and a data element of type value, integer in this case. So we've declared s, we've said s.top equals 0. Now let's push the number 28 onto the stack. Well, what does that mean? Well, currently the top of the stack is 0. And so what's basically going to happen is we're going to stick the number 28 into array location 0. Pretty straightforward, right? That was the top, and now we're good to go. And then we need to change what the top of the stack will be. So that the next time we push an element in, we're going to store it in array location probably not 0. We don't want to overwrite what we just put there. And so we'll just move the top to 1. That probably makes sense. Now, if we want to push another element onto the stack, say we want to push 33, well, now we're just going to take 33 and put it at array location number 1, and then change the top of our stack to be array location number 2, so that the next time we want to push an element onto the stack, it'll be put in array location 2. And let's do that one more time. We'll push 19 onto the stack, so we'll put 19 in array location 2, and change the top of our stack to be array location 3, so that the next time we need to make a push, we're good to go. Okay, so that's pushing in a nutshell. What about popping? So popping is the sort of counterpart to pushing. It's how we remove data from the stack. And in general, pop needs to do the following. It needs to accept a pointer to the stack. Again, in the general case, in some other case, you might have declared the stack globally, in which case you don't need to pass it in because it already has access to it as a global variable. But then what else do we need to do? Well, we were incrementing the top of the stack in push, so we're probably going to want to decrement the top of the stack in pop, right? And then, of course, we're also going to want to return the value that we remove. If we're adding elements and we want to get elements out later on, we probably actually want to store them so we don't just delete them from the stack and then do nothing with them. Generally, if we're pushing and popping here, we want to store this information in a meaningful way, and so it doesn't make sense to just discard it. So this function should probably return a value to us. So this is what a declaration for pop might look like there at the top left. This function returns data of type value. Again, we've been using integers throughout. And it accepts a pointer to a stack as its sole argument or sole parameter. So what is pop going to do? Let's say we want to now pop an element off of S. So remember I said that stacks are last in, first out, LIFO data structures. Which element is going to be removed from the stack? Did you guess 19? Because you'd be right. 19 was the last element we added to the stack when we were pushing elements on, and so it's going to be the first element that gets removed. It's as if we said 28, and we put 33 on top of it, we put 19 on top of that. The only element we can take off is 19. Now, in the diagram here, what I've done is sort of deleted 19 from the array. That's not actually what we're going to do. We're just going to kind of pretend it isn't there. It's still there in that memory location, but we're just going to ignore it by changing the top of our stack from being 3 to 2. So if we were to now push another element onto the stack, it would overwrite 19. But let's not go through the trouble of deleting 19 from the stack. We can just pretend it isn't there. For purposes of the stack, it's gone if we change the top to be 2 instead of 3. All right, so that's pretty much it. That's all we need to do to pop an element off. Let's do it again. So I've highlighted it in red here to indicate we're making another call. We're going to do the same thing. So what's going to happen? Well, we're going to store 33 in X, and we're going to change the top of the stack to 1. So that if we were now to push an element into the stack, which we're going to do right now, what's going to happen is we're going to overwrite array location number 1. So that 33 that was sort of left behind that we just pretended isn't there anymore, we're just going to clobber it and put 40 there instead. And then, of course, since we've made a push, we're going to increment the top of the stack from 1 to 2 so that if we now add another element, it'll go into array location number 2. Now, linked lists are another way to implement stacks, and if this definition on the screen here looks familiar to you, it's because it looks almost exactly the same, and in fact, it pretty much is exactly the same as a singly linked list, if we recall from our discussion of singly linked lists in another video. The only restriction here is, for us as programmers, we're not allowed to insert or delete randomly from the singly linked list, which we could previously do. We can only now insert and delete from the front or the top of the linked list. That's really the only difference, though. This is otherwise a singly linked list. It's only the restriction we're placing on ourselves as programmers that changes it into a stack. The rule here is to always maintain a pointer to the head of the linked list. This is, of course, a generally important rule for singly linked lists anyway. You only need a pointer to the head in order to have that chain and be able to refer to every other element in the linked list, but it's particularly important with a stack. And so generally you're going to actually want this pointer to be a global variable. It's probably going to be even easier that way. So what are the analogs of push and pop, right? So pushing, again, is adding a new element to the stack. In a linked list, that means we're going to have to create a new node that we're going to add into the linked list, and then follow the careful steps that we've outlined previously in singly linked lists to add it to the chain without breaking the chain and losing or orphaning any elements of the linked list. And that's basically what that little blob of text there summarizes, and let's take a look at it as a diagram. So here's our linked list. It currently contains 4 elements, and more appropriately, here's our stack containing 4 elements. And let's say we now want to push a new item onto this stack. And we want to push a new item whose data value is 12. Well, what are we going to do? Well, first we're going to malloc space, dynamically allocate space for a new node. And of course, immediately after we make a call to malloc, we always make sure to check for null, because if we got null back, there was some sort of problem. We don't want to dereference that null pointer, or we will suffer a seg fault. That's not good. So we've malloced the node. We'll assume we've had success here. We're going to put 12 into the data field of that node. Now, do you recall which of our pointers moves next so we don't break the chain? We have a couple of options here, but the only one that's going to be safe is to set new's next pointer to point to the old head of the list, or what will soon be the old head of the list. And now that all of our elements are chained together, we can just move list to point to the same place that new does, and we have now effectively pushed a new element onto the front of the stack. To pop, we just want to delete that first element. And so basically what we have to do here, well, we have to find the second element. Eventually that'll become the new head after we delete the first one. So we just need to start from the beginning, move one forward. Once we've got a hold on one forward of where we currently are, we can delete the first one safely, and then we can just move the head to point to what was the second and then now is the first after that node has been deleted. So again, taking a look at it as a diagram, we want to now pop an element off of this stack. So what do? Well, we're first going to create a new pointer that's going to point to the same spot as the head. We're going to move it one position forward by saying trav equals trav next, for example, which would advance the trav pointer one position forward. Now that we've got a hold on the first element through the pointer called list and the second element through a pointer called trav, we can safely delete that first element from the stack without losing the rest of the chain, because we have a way to refer to the second element forward by way of the pointer called trav. So now we can free that node, we can free list, and then all we need to do now is move list to point to the same place that trav does, and we're sort of back where we started before we pushed 12 on in the first place, right? This is exactly where we were. We had this 4-element stack. We added a fifth, we pushed a fifth element on, and then we popped that most recently added element back off. That's really pretty much all there is to stacks. You can implement them as arrays, you can implement them as linked lists. There are, of course, other ways to implement them as well. Basically, the reason we would use stacks is to maintain data in such a way that the most recently added element is the first thing we're going to want to get back. I'm Doug Lloyd. This is CS50.